This podcast in the gas calculation section is relating temperature and volume. If you have a sample of gas under constant pressure, at this time the pressure is 10, and you heat it, it will expand because the particles are moving faster, and every collision with the walls of the container exerts more force, and so the volume necessarily must go up. And we say that temperature is directly proportional to volume. Let's look at a sample problem. Here we have a 2-liter sample of gas at a constant pressure, initially at a temperature of 295 Kelvin, and we raise the temperature to 400 Kelvin. And we want to know what's the new volume of the gas. The solution is, as always, write down what you're given and label your variables. The initial volume, V1, is 2 liters. V2 is the unknown. T1 is 295 Kelvin, and T2 is 400 Kelvin. So our solution is to take the initial volume, because we're looking for a volume in the final answer, so we use a temperature-based conversion factor. And now, since we know it's directly proportional, we're going to want to have a fraction that has the larger number on top, because, indeed, the volume is going to go up. So we have 400 Kelvin over top of 295 kelvins, and we get an answer at 2.71 liters. Now, once again, because they're directly proportional, the V has to go up, and we use what we call a top-heavy fraction in this calculation. And the final value, 2.71 liters, is greater than 2 liters, and it makes sense. Similar example, here we have 4 liters. Now, this time the temperature is still 295, but the conditions are altered and the volume drops from 4 to 2.5 liters. Again, what's the new temperature? Initial volume is 4 liters, final volume will be 2.5. Initial temperature is 295 Kelvin, and T2, the final temperature, is our unknown. So again, this time, we're going to have a conversion factor involving the volumes. But now we know that the volume has dropped, so we're going to want a bottom-heavy fraction with the 2.5 liters on top, the 4 liters on the bottom, and we end up with 184 kelvins. The volume was decreased, the temperature has decreased. These are directly proportional, and so we have to use this bottom-heavy fraction in the calculation. The final value, again, makes sense. It is less than what we started out with. That means the particles are moving slower, which makes sense. This is actually called Charles' law, that volume is proportional to temperature. It was named after Jacques Charles, who first produced it or discovered it. He was a balloonist in France and someone who actually studied a lot about gases.